Hi, could you unmute it? It's muted. We cannot hear anything.
Okay, success. All right. So if you haven't heard of Boston Dynamics, we're in Waltham, Massachusetts. We're currently owned by Hyundai. We have at least 700 people, although I think that might be out of date. We might have 800 or 900 by now. We're growing across the board. So if you want to come and work on robots, this is a great place to come and work on robots. We have Spot, which is an autonomous platform for doing things like inspection, data collection, manipulation. We have Stretch, a robot for moving boxes and other things inside warehouses. And we have Atlas, which is primarily a research and development platform that we're slowly working on turning into a product. All right, so what I want to talk about today. First of all, I want to go over how we use MPC on Atlas. Just saying that we do everything with MPC isn't enough. I want to give an idea of how we use it and the variations that it's taken over time. What have we learned from doing that? What are the challenges? What problems have we run into? What things do we maybe know how to solve and what don't we know how to solve? And then a little bit about where are we going next. All right. So we've been using MPC on Atlas for anything you've seen in a video since about 2019. So our parkour, our floor routine gymnastics, we've shown it for dancing, including dancing together. We've shown MPC for doing things like coordinated backflips and running over parkour courses. More recently, we've shown MPC for manipulating objects, including objects that are relatively heavy, that have inertia that matters relative to the inertia of the robot, doing things like throwing, pushing, and silly jumps. And as of this year, we've secretly been working on a brand new robot, which I'm very excited that I can finally talk about, the new all-electric robot, which is still powered by MPC and an evolution of the same controller that you've seen running on all of the hydraulic robots. Common across all of the versions of MPC that I'm going to talk about are a few features. All of them have nonlinear dynamics from the start. There's nonlinearities everywhere, especially in things like the coupling between the location of a contact and the amount of force applied at that contact. We're just going to embrace that. Everything's going to be nonlinear. We're not going to find a single perfect linear approximation of the system. It just is nonlinear. We're going to resolve that by iteratively linearizing. So we have a solution, initially just a guess. We're going to solve a QP and then linearize around the solution of that QP. We're really not interested in running to convergence. I think philosophically, the convergence is an interesting thing, but it doesn't matter that much because I don't find it that predictive of whether the robot actually worked. It's not worth spending 100 more time waiting for convergence to some arbitrary threshold if the robot fell over while you were waiting. On the other hand, we are going to do a lot of work exploiting problem structure for speed. We have a lot of sparsity that's implied by the way the MPC problem is structured, and we're going to try to preserve as much of that sparsity as possible. And we're going to try to avoid being afraid to open up the solvers. So we'll take the solver apart, rewrite its internals if we have to, really whatever we can do to get more performance out, because at the end of the day, we need to solve the biggest MPC problem we can as fast as possible. And just for context, I napkin math that I think we've solved about 10 million QPs on robots since I've been there, and probably about 10 billion QPs in simulation. So we've done a fair amount of MPC, but it's not nearly enough. All right, so we started with just thinking about the robot as a potato. That's already pretty hard. That's something that in grad school I would have told you was too hard because it's nonlinear. You've got this coupling between the location of a force and the amount of force. You've got all the rotation dynamics. It's too hard. We're just going to do it anyway. Iteratively linearize, solve QPs. And that works pretty well. So we can have the robot do something like spin around in a 360. If we just change the axis of rotation, we can just do the same thing and call that a backflip. And really what we're doing here is mostly MPC over just the dynamics of a potato. And with something like the backflip, we have a reference that at least gives us an idea of how big the potato is as a function of time. But to do something a little bit more complicated, we need to start thinking about the limbs. I mean, the robot is not a potato. It has limbs. Those limbs can move. And so where we went was a staged optimization. So thinking about the motion of the potato, think about the centroidal dynamics, and then run some downstream optimization over the kinematics. Try to find some kinematic behavior that's consistent with the potato. And when that works, it's really cool. We can do things like, leaping over this beam where we're using both the hands and the feet to manipulate the centroidal dynamics, but moving the limbs in a way that we track a reference trajectory that keeps us clear of the beam. Uh, but the problem here is, well, what if the potato tries to do something that the limbs just can't do? And the answer is that the robot fails, and often quite spectacularly. Once you have jumped, there's only so far you can get. And if you can't get the limbs to the other side of the platform, there's nothing to be done. And so the problem was that prior to leaving the ground, you should have been pushing harder, but the potato thought it was fine. And so the potato was wrong. And so where we went from this is treating the robot as a coupled kinodynamic system. So thinking about a single optimization that covers the robot's centroidal dynamics and its full kinematics. And that at least allows you to avoid problems where the potato tries to put the mass somewhere that the legs can't reach. And this was required to do things like what we called the sick trick. So this inverted 540 or whatever it is. This really wasn't possible with any of the previous versions of MPC. One of the cool things I think that you can see in this video is that we're not just tracking a reference perfectly here. There's an arm motion that happens at the end of this behavior where the robot flings its arm around in a circle. And that's just an emergent behavior from the optimization. So that's the solver trading off a little bit of error in joint space to put some angular momentum into the arm temporarily so that it can pay that off later and not fall over. And that's just something that wasn't really possible for us with these staged optimizations. And this kind of led to a lesson that I think we've been seeing, that we haven't found a limit at which model complexity stops helping, except in that it makes all of your computation harder and your software bigger. As we add more things to the MPC problem, as long as they are correct, they seem to help. If they correctly represent the limits of the system, they tend to improve performance. But they take more compute and they're harder to get right. So, oh, come on, Google. All right, I'll read the tab. If it doesn't play the video, it's not the end of the world. So in order to get the robot to manipulate objects, we kind of took the same approach, which is, well, we could plan a separate motion of the object and then try to find a motion of the robot that's compatible with that. But the motion of the object that we're manipulating is constrained by the motion of the robot, and the motion of the robot is constrained by the motion of the object. So we might as well just solve them together. And so that's what we did. We put the entire state of some object that we are manipulating into the same MPC problem. We just made it bigger and then added constraints that describe the state evolution of that object and the relationship between the state of the robot and the state of the object. And this is what allowed it to do things like throwing a tool bag, carrying a plank, manipulating objects that are relatively heavy. But of course, that's not enough, because everything we've shown you before is in these very structured environments, mostly just flat planes. So now we need to start thinking about the world that the robot is actually in. And again, we're just going to make the problem a little bit bigger and a little bit harder by introducing things like constraints driven by perception. So we're going to take something like a voxel map representation of the world and just throw that into the MPC problem as an additional constraint. So keep all of your limbs outside of this voxel map. And so in this example, we're telling the robot to jog straight forward. There's no reference to do anything in particular, but just by requiring it to keep its head outside of the voxels, it figures out to duck down. It's still a local optimization. There's nothing magic here. It's not going to do a particularly smart job of deciding which way to go around a tree. If you drive it directly at the center of a tree, it will probably just stop. And if you drive it vaguely to the right, it will continue going to the right. It's still local. But it's been surprisingly effective to just rely on these local optimizations and see how far we can get with that. And on the left, I have a frontal video of the robot running directly towards a box and using some clever hip inversion to get all the way around it. This is both a challenge and an opportunity with this robot with its ridiculous range of motion, that it can wrap itself all the way around in order to avoid an obstacle. But even that's not enough. I mean, walking around and doing some pre-scripted routine is fine for making YouTube videos, but it doesn't actually create a robot that's useful for doing tasks. And so another thing that's been a big challenge for us recently is taking this entire system of MPC and hooking that up to some kind of task that you'd want to specify online. And so as an example, here's the robot doing teleop. And so we're taking the motion of the operator's hands and transforming that into a reference trajectory for MPC. But of course, we don't know what the operator is going to want to do in the future. So we have to play some games to turn the instantaneous pose of their hand into a time-varying reference for MPC. And likewise, we might have some autonomous behavior we're trying to execute, like looking at a fixture and walking towards it. And again, we're taking these inputs from sensors that might be coming in asynchronously and online and using those to build references for MPC, and which means that MPC has to be very tolerant of the reference completely changing from one moment to the next. All right, so what are some of the lessons we've learned? As I said before, so far, more complex models keep working. And I think there are several forms of complexity that I would like to add to our models that we just don't think we have compute for yet. I would have told you in grad school that combining centroidal dynamics and full kinematics would be too nonlinear. I don't know what I would have meant, but I would have said it. I would have told you that it was numerically bad or wouldn't converge, and I would have just been wrong. And so that's been interesting and humbling. So far, combining things has generally worked better. And I think the fundamental lesson is that you really don't want to throw away gradients. So when we separated our kinematics and our centroidal optimizations, there was no way to inform the potato that the limbs couldn't do something. And so those gradients were carried over through our engineer brains by redesigning behaviors to sort of stress the system less. And it's a lot more efficient to just let those gradients be actual gradients and let your solver sort of work its way downhill rather than you working downhill yourself. Another cool example of that is this, this video of the robot being hit by a basketball traveling at 20 meters per second while balancing on one foot. If we give the robot a model of a pole that it's holding, it's able to exploit the dynamics of that pole to preserve balance in a way that it can't without that. We've tried to do that with staged optimizations or separation, and we've never really gotten a successful example. It required putting the model of the object we're interacting with and the model of the robot together into the same optimization to make that work. Another thing that's been relatively surprising is that we're getting pretty good performance out of just nonlinear MPC in ways that you wouldn't necessarily expect to converge. The non-convexity of things like the location and force of a contact, I'm sure we are hitting local minima, but they're often quite good. And I think when the robot fails, it is not because we have failed to solve that particular non-local issue. It's because our model is fundamentally wrong in a way we haven't captured, or we're failing to make useful decisions like changing mode sequences. Just to give some examples, here's the robot being pushed. This is a person pushing the robot basically as hard as he possibly can and doing step recovery. We're not telling MPC what to do. We're just telling it to stand still and then giving it just a sort of heuristic left, right stumble sequence. But all of the location and the amount of force that it's choosing, all of the arm motion, all the leg motion is just a local optimization. Unless you think we're overfit to being upright, we can also do some more silly things very far from our nominal posture. Multiple contexts, not really a problem. They're just more decision variables in MPC. This is running the same MPC that we run for everything else. And just in case you were overfit to locomotion, we're obviously happy to flip that around. I'm sorry, I don't have a real robot video of this yet. Okay, so from an engineering perspective, careful engineering, I think, is what makes MPC actually work. The math is all sound, but to get it into a robot that actually runs and have it run 10 billion QP solves takes a lot of work. Software performance is really important. If your answers are too late, they're not useful. But I think yeah, and there are various things we can do, warm starting, cache awareness, et cetera. But software correctness is a lot more important. If your optimization gives the wrong answer because you have a sign error, it's just not going to work. Or worse, it will work, but poorly, which is, I think, what usually happens. And maybe a better summary of this is that a mathematically bad idea is indistinguishable from just bad code until you find the bug. And I suspect that we as a group are missing some interesting ideas that were good ideas and do work, but we got the sign wrong somewhere and we discarded them. And so it's always worth going back to that idea that you thought could have worked like 5 years ago and just maybe try doing it again because maybe you just got the sign wrong. I've gotten a lot of signs wrong. And the other thing is that I feel like robot performance for us is the objective. Everything else is just a proxy. And what I mean is, convergence of the solver, I don't care. Like, I care about whether the robot did the backflip or not. there are useful proxies, and you need them in order to make progress on the problem and to get from literally nothing to can backflip. But I think it's important to sort of keep whether the robot did the behavior is ultimately the objective that you're trying to optimize. Another thing that I think we've learned is that pretty coarse trajectories are surprisingly good references. So we encode all of the behaviors that we do as trajectories. So we have some desired joint space motion over time, some desired end effector poses over time, some desired object pose over time. And they can be, and almost always are, totally inconsistent, aphysical. So we're asking for the robot to slide forward while picking up its feet. That doesn't make any sense. But it works sort of okay. And what it means is that we can run the same MPC for everything. So with very little tuning per behavior, we're just running the same controller with different flavors of reference. So for something like walking, we would tell the robot, slide forward and have your feet sort of pick up and down, and expect that MPC is going to find a walking motion out of that. For something like manipulation, we might layer a motion of an object on top of some reference motion of the robot, neither of which is actually physical, and they don't match with each other, and just tell MPC to do both at the same time. And with like an appropriate scheduling of weights, we can get MPC to do something physical that unifies the two things that we asked it for. And I think what this creates is a challenge for us as controls engineers is the better your controller is, the worse references it can take. And I think that's a useful metric. You want your MPC to be as good as possible as taking in references that make almost no sense and producing something that's physically realistic. Okay, so trajectories are a great way to encode behavior for MPC, but they're also really hard to produce. We have to define some kind of cost function that we want, maybe just stay close to this particular joint space motion. But what if the robot's behavior can switch depending on what happens? So, imagine that we're going to walk to something, and then if we get there, we're going to reach, and if the reach is okay, we're going to grasp, and if the grasp is okay, we're going to lift, and we're here, we're halfway through reaching. What is the reference trajectory for MPC here? Well, does it include grasping? We don't know if we're going to grasp until we know if we actually reached the object that we're supposed to reach. So should MPC be sort of looking ahead to grasping and lifting? But that's too optimistic. Should it be looking ahead to assuming it will fail and walking? It's probably too pessimistic. Should its cost function include the switches in this graph? Maybe, but now it's discrete in an awkward way. And this discretization is arbitrary. It could do a lot of other things. I don't know an answer to this. Another challenge is, we've had a lot of success with local optimization, but it still fails. We can get the gradients that steer us the wrong way around. We have a lot of range of motion, so there's a lot of wrong ways around on this robot. And in particular, we fail when we don't get the contact modes correct. So we have some heuristic mode that we expect, and when that doesn't happen due to a collision that we didn't expect or missing a collision that we do expect, the robot just fails. So how do we let MPC pick a mode sequence to recover from this rather than just failing catastrophically? I don't know. And then the remaining challenge for us is continuing to scale. So how do we add more complexity? I think complexity is helping us. Bigger models are helping, but we only have so much CPU available. So how do we make the most use of the CPU that we have? And then how do we decide what additional complexity to add? We have some modeling of actuator torques, but I think we need more. We have some modeling of our closed chains in the robot, but we need more. We definitely need some kind of contact implicit optimization so we can choose mode sequences. It would be great to represent the uncertainty we have about our own state or our model in MPC. And then how do we use the advances in computing hardware to make this possible? So we're doing a lot of work on things like porting MPC to the GPU, but that's a hard open problem that we're still working on. All right, so what's next for us? I think the unification of MPC and machine learning is the biggest thing on our horizon. And we don't know exactly what form that's going to take, so we're going to try all of them at the same time. So one of the things MPC can be is a data collection platform. We can just run the robot around because we have a pretty robust controller for walking around and doing stuff. And so we can use that as a way to gather data. We could also potentially use MPC as an API. So rather than an RL policy having to talk directly to the joints, it could talk to MPC as a sort of abstraction of the capabilities of the robot. We could try to distill MPC down, using it as a teacher to train some policy that we can evaluate more efficiently. Or maybe MPC is just a technology that we hold on to, and eventually we reward hack our way to something in RL that just strictly works better, and then we switch to that. I don't know. And we're exploring all of these in different directions, things like, in things like teleoperation, things like taking motion capture data and turning that into robot behaviors, gathering examples of manipulation to train policies, and even just walking around the robot to gather data about trying to learn a better model of the robot and its controls. So if these things sound interesting to you, we are still hiring people to do all sorts of interesting robot tasks. And I'm happy to take your questions, and thank you.
Thanks for the excellent talk. I was wondering a little bit about how you decide the replan rate of your MPC. So you mentioned that you don't really run to convergence or aren't necessarily concerned with running to convergence. But it seems like there's some trade-off between kind of like how often you replan and like how close you can get to convergence. So like, how do you make that decision?
Yeah, that's a really good question. So you're right. There's a trade-off between accuracy of the result, which you can just spend more time to get a better result, versus latency of the pipeline. I actually optimized it. I wrote a sort of brute force optimization over running simulations of the controller under various solver parameters. So parameterizing the accuracy of the solver, the number of iterations, and then simulating the latency that would imply, and then tried to close the loop on, did the robot do the backflip? I think I was looking at jogging, but have the robot jog forward and see how close it was to minimizing some objective that we actually cared about. Yeah, so empirically was the answer to that question. I don't know of a better way to do it, but I think that is what I care about, is whether the robot did the thing. And so that's what we measured.
Thank you very much for a very interesting talk. So I have a question regarding this kind of, you mentioned as a heuristics for kind of footsteps planning and these things. So how much that influences and how much that is kind of constrained to this kind of local minima?
Yeah, I think the contact planning is the biggest thing that the MPC can't do for us. And so it is really important to give it something at least vaguely reasonable. What we're doing now, I think, is pretty basic. When we're walking forward, the contact sequence is just a left-right tape. One of the advantages we have is that our MPC is allowed to scale time. And so it can speed up or slow down events. It can't change the mode sequence or reorder things, but being able to stretch time buys you a lot of flexibility. It frees up the footstep planner from having to choose how fast you're stepping. I think that's really important. Having tried to do optimization over footstep placement and timing outside of an MPC a long time ago, I found that to be really hard. And being able to just let MPC figure out part of that helps. But we mostly fall over because we tried to stay still, and we should have just taken a step. If the robot were always stepping, it would almost never fall over. And the only reason we don't is that if you're always stepping, you get a lot of motion blur and it looks kind of dumb and you waste a lot of power. But like from a controls perspective, if we were just always stepping left, right very quickly, it would be almost impossible to knock this robot over.
Thank you. This is a super naive question from someone who's not in this area, but like you were talking about convergence and, time versus accuracy and all of that. Have you considered a sort of an adaptive version of that, equivalent, I suppose, to our like adrenal response when we trip, such that you estimate how long you have before things go pear-shaped and then be more or less accurate, demanding whatever in response?
No, we've never thought about that, but I like that idea. One of the things that we're limited by is heat. Like the CPU can go faster in bursts than it can sustained. We are not scheduling the throttling of our CPUs based on our level of concern about whether we're falling, but we totally could. I don't know if the timescales of how long you have before the CPU overheats align with the timescales of not falling over, but they might. We could kind of like that. Yeah.
So maybe a last question. Okay, I will go the closest.
Thank you. I had a question on basically the role of dynamics in MPC. So I was wondering how good your potato model is to the actual physical system, and how much does that matter? So for example, if your system is 15 kilos, is your potato 15 kilos, or could 12 kilo potato actually give you the system?
It's hard to summarize the accuracy into like a single number. One of the things I look at a lot is, a plot of the predicted position of some joint 1 second in the future, and then compare that to where that joint ended up 1 second in the future. And often it's quite good. Like when things are going well, it's pretty accurate. And I think we're relatively tolerant of mass errors. If the robot's under by 10 kilograms, it's not a huge deal. It degrades performance, but it's not a catastrophe. But there are other ways in which it turns out we're really sensitive. If the robot is compliant in ways that we're not modeling, that can make state estimation and control hard in ways that introduce instabilities that are just totally outside of MPC's domain. And that kind of thing can just completely void your predictions. So when things are going well, it's good, and then it's not.
So thank you again, Robin, for the nice talk. Can you set up? Okay. So the next speaker is Marc Toussaint. So Marc Toussaint is a professor at TU Berlin. And today he will talk about NLP sampling, combining MCMC and NLP methods for diverse constraint sampling. So thank you, Marc.
Okay. Unmute here. Okay. Thanks very much for inviting me. It's really exciting. This was a great line of speakers, so I'm under a bit of pressure. So let me jump into the motivation before I talk a bit more about the background of this work. So the motivation for this line of work and for what I'm going to talk about today is that for a couple of years, we've been working on task and motion planning. This talk is not really much about task and motion planning, but we kind of worked on formulations of task and motion planning that build on NLP solvers, on constraint optimization solvers. And so with that background, we use these solvers very often to solve subproblems of a larger problem. So task and motion planning, we've heard it already, is a hybrid problem where you search over discrete decisions, and then subject to that also have to solve some nonlinear mathematical programs. And in principle, we have to solve many of these subproblems. For instance, subproblems that are about, is something reachable? Is there an inverse kinematic solution? And so forth. And then try to piece these solutions together.
The point that I wanted to make is, in the context of our solvers over the years, what we ran into very, very often is that we actually want the solvers to return a whole diversity of solutions, not just one. So if these sub-solvers just return one of these solutions, that's often not really helpful for the overall solver. In particular, if you want something like probabilistic completeness and so forth. And so point being is, this is a really big motivation for me to look into, can I not use, the strength of mathematical programming solvers, but actually make them generate a whole diversity of solutions. And then in a completely different line of thinking, in the last year and so forth, so much have been happening on completely different lines of search, like diffusion models and denoising and so forth. I work a lot with mathematical programming solvers, but on the other hand, we have MCMC, Markov chain Monte Carlo methods that generate globally if only the mixing wouldn't be a problem, right? And then there is Stein variational and gradient descent, which also globally approximate a distribution. Then there is diffusion denoising, which is kind of amazing in its capability to take an initial single mode distribution and then transport that probability mass globally to all the kind of modes that the problem might have, right? And I was wondering, and actually motivated initially also to think, what's the bigger picture here? Why is there this one field, mathematical programming, super efficient to go in just one point, and then the other field talking about generating diverse solutions? Is there not a joint view on both of these kind of fields? And well, in principle, I was thinking about whether we shouldn't treat and also understand optimization sampling methods more jointly, transfer ideas between them and so forth. Okay, the initial ideas were actually failed. And also at the end of the talk, I'm going to talk a bit about these failures. Maybe it's also nice sometimes to talk about what didn't work, right? I think now it's completely clear why it didn't work. And what I'm going to talk about today is really very fresh ideas. There is no conference paper yet published about this or anything like that. Actually, in contrary, I kind of took the occasion being able to give a talk here to write a paper for this talk, kind of to prepare myself for this talk, right? So the whole thing that I'm going to talk about, I wrote this in this paper before just to put my thoughts together. So you're welcome to look into that paper. And yeah, so the idea of the talk is also to get feedback. So many of these ideas might still be naive, and I'm wondering if some of you think they are naive or super fresh. I'm really curious actually to learn what do you think. So let me get started. NLP sampling. I started with this word, and everybody thinks it's about natural language processing. No, it's about mathematical programming. You all know what is an NLP, fine. Why do I combine that with sampling? Well, I define this problem here that I want to sample from a distribution, which takes what we usually call as cost as the energy. So we have a probability distribution with the energy F. And the constraints just, multiply hardly to give zero probability. So these are inequality constraints and equality constraints. And the setting is very much as we are used to in optimization. So we only allow pointwise access to these functions, so we can create these functions at some point. We don't have a priori data from whatever. And so how can we solve that? And I mean, first thing is there other methods already around? Is there has this problem been treated before? Okay, some notes. If there is only linear inequalities and nothing else, that's actually called polytope sampling. There is interesting work on polytope sampling. I'm mentioning some stuff like hit and run. There is also other interesting work. So whatever we come up with as good solvers for that should definitely also cover these kind of behaviors that polytope sampling does. Then there is manifold sampling. There is really interesting works also manifold, like Hamiltonian methods that work on Riemannian manifolds. Other kinds of the robotics community has very interesting work, manifold RRTs. So whatever we come up with being efficient on this problem should also be efficient on these kinds of problems, right? There's other little obvious things, like if you try to naively apply whatever MCMC or Langevin or whatever Stein variational methods on this problem, you immediately see, hold on, the probability is flat zero outside the feasible space, no score function, no gradients. Okay, naively it doesn't really work. So we need to have some kind of ideas to I don't know, solve this problem. The first, So this is my approach that I kind of like followed eventually, that in the paper that kind of worked. Later, I told you already, I also tell you about the approach that didn't work, right? But here is like a really down-to-earth approach that worked. And it's completely like following maybe the standard reasoning that you would also find, you know, in kind of textbooks, maybe about optimization. So the first idea you might have is to say, let's relax the problem. Let's define something. I call this here the slack vector, which is just the stack of all the constraint violations. So this is the inequality constraint violations and equality constraint violations, and define the relax problem to have another energy, which is, you know, has the original energy F as a scaling, and then also has the square penalties here as the second term. And you can guess already why I put it in this form, because then later on we can use Gauss-Newton methods for this kind of term. A bit unusual is that I put coefficients in front of both of these terms. Why is that? Well, because if I set this one to 0, so I ignore like the original energy completely, assume it's flat, and only care about, you know, slack reduction, then I'm completely into phase 1 optimization in the classical thinking of optimization, right? So phase 1 would be slack downhill. And then if I set this one here to 1 and this one like super high, then I'm more into a regime that I now start really caring about the energy in the interior space and have a very high penalties, you know, to not escape the interior, which is what in the paper then I started calling interior sampling. And I thought this is like a super, you know, straightforward framework to actually now have a very rich set of possibilities of how I can solve these kind of problems by thinking about different methods for slack downhill and interior sampling. And the obvious approach now that that I will, you know, show and also like show some results about that is now to think about what kind of algorithms can I design which are restarting two-phase NLP samples. So I kind of like use informed restart sampling. I mention what kind of methods I use later, and then use slack downhill to just find a feasible point. And there is all kinds of methods for slack downhill for that. And then I think about what are methods for interior sampling. And that's a very generic framework to now integrate ideas from all over the place, from robotics, MCMC, and also from the optimization literature. Okay. Now, the first set of methods is like really textbook kind of building blocks, but they already span a really wide range of possibilities what you can do. On the next slide, I will have some things that are a bit, you know, not so straightforward, but this one is really just kind of textbook building blocks of how to put together a sampler. So for both downhill and interior sampling, it doesn't really matter. It only matters that we have an energy. You could decide to design a method that combines gradient steps, go downhill, of course. You can decide to use plane gradients or Gauss-Newton steps actually to go downhill. You can decide to add noise. There's different types of adding noise, isotropic noise, also covariant noise. Covariant meaning covariant with the Hessian of this energy. And you can also decide to do step rejection, like Metropolis Hastings, if you are more coming from MCMC, or kind of first Wolf condition or Minja rule, if you come more from the optimization. You know, very basic things, and you put them together, and then they can be used both for downhill and also for interior sampling. A couple of notes on that, and this was more like a learning experience I had when I did this, and I wonder whether it's obvious to you. Some things are obvious, like Langevin, for instance, that's of course a special case of that. You use gradient steps, isotropic noise, and use Metropolis Hastings typically to adjust that it's like really sampling from the proper one. There is also what is called Riemannian Langevin. Girolami, I think, also published on that. It's actually also a special case of that. It's really equivalent to using Gauss-Newton steps and then using covariant noise, but also using Metropolis Hastings. Okay, so all of these like things are kind of like special cases of the kind of method that we have here. And also I learned there's actually an interesting relation that I never came up with seeing anywhere. So when you think about what is the Metropolis Hastings step acceptance probability, and you know, just check what it is for typical noisy gradient steps, it turns out it is almost equivalent to the Minja rule. And I didn't really know that, you know, backtracking line search is so closely related actually to Metropolis Hastings adjustment of these kind of things. Okay, I just mentioned this. So this spans kind of like one space of possible methods to do both downhill and interior sampling. And then I also looked into, acknowledging what I said earlier, that there are special methods for polytope sampling or for manifold kind of like sampling, and try to also integrate those. So for manifold sampling, and I don't talk more about this here, I in particular looked at what robotics people like proposed, and it also turned out really efficient, basically doing RTs on a constrained manifold, on a Riemannian manifold. And for polytope sampling, or when we have inequalities, I found hit and run actually super interesting, because unlike all the other kind of MCMC methods, hit and run is super explorative. And maybe I should mention, I don't know if people don't know hit and run, what it actually does. So if you have a polytope, like a feasible polytope, you start at some interior point, hit and run would select like some random direction. And this is really a random like vector direction, would try to compute the intersection of that random direction with the polytope, which is these 2 points, and then sample uniformly on that ray. And that's really super explorative, and it's quite in nature, quite different to all the kind of local, whatever, Langevin or kind of like gradient or whatever kind of steps. It's super aggressively kind of exploring the space, which is interesting. But the existing hit and run only works for really linear inequalities. So in that paper, I also thought about how to generalize that into a nonlinear case, and also to generalize it to the fact that we actually have an energy in the interior. So, it's not that we want to have uniform samples in the polytope, but actually have an energy there. And okay, I'm not going to go through that pseudocode here or whatever, but you can imagine that it's doable to kind of generalize it, right? And also like include this Metropolis Hastings term to actually account for an energy in the interior. Okay, so let me discuss through a couple of results, and then maybe have some bit more time like for the higher level discussion at the end. So I start with some simple kind of plots, and these are always like these kind of scatter plots, just to give you an intuition of how this works and how these methods actually behave. And the first plot is exactly obvious, kind of like that's how you expect how it behaves. If you just do like slack downhill, so only phase one, aggressively reduce. Oh, by the way, here the problem is to sample from a box. You have 4 inequality constraints, and you want to sample in the interior, but the initialization, like the space is like this one. If you only use downhill, then you will end up always at the margin of the feasible space. So that's an obvious thing, that the downhill methods always bring you to the margin of the feasible space. And then the question is whether you can do very quick, efficient mixing also inside the interior space, right? That's kind of obvious. So this is without any interior sampling. If you just do a single hit and run step after this, actually, you get very good mixing already in the interior. If you just do 2 hit and run steps, you get very, very actually mixing inside the interior of that thing. So that's the little story here. That's kind of obvious. Really quick also here, if you add some kind of energies in this side, so you can check whether they're all like consistent and lead to the same results. You can compute earth mover distances between the ground truth distribution and the actual sample one. And they basically, like also the nonlinear hit and run, MCMC, Langevin, they basically all in these simple cases generate the same kind of samples. They're consistent, all fine. Let's get more into the whole diversity topic. So when you have problems with many, many modes, and this is one example of problem with many modes, where in the space, in every corner of the space, there is a mode, and then in the center of the space, there is also a mode. The question is whether our samplers can discover all of these modes. In a 2-dimensional space, there's only 5 modes. In a 6-dimensional space, which is here, there's already 56 kind of modes. And the more like in higher dimensional space, there is many, many modes you can sample. So in a 2-dimensional space, again, if you just do the slack downhill only, then you only reach the boundary of the feasible space. If you do some interior sampling, then you can also get diversity in the interior space. If you go to higher dimensions, basically, you pretty quickly see that the modes at the corners are not discovered anymore. So this is not really diversity sampling. If you use some initialization, like seeding, that is always accounting for the samples you've taken already, and seed your method very far away from those, you actually also discover these kind of modes, which this method is doing. Okay, at that point, maybe it's not fun anymore to look at the scatter plots, and we want to have a proper metric, right? A quality, my method is better than yours, something like that, right? And that's a tricky one, actually. Earth mover distance would be cool if we could really compute it, right? then let me, next slide. So the question is, what is actually now a metric that I can show you and say, look, this is cool, this is better, this is worse, and so forth. It's actually surprising if we talk about, when it's about diverse sampling. So if we had a ground truth and we can compute something like a true divergence measure, like Earth mover distance, that's cool, but that really doesn't scale at all. Most of the metrics that are actually around in literature, turns out that they kind of like look at the local spectrum, like look at the local neighborhood distribution, whether it's equidistant and things like that. But they would never capture actually whether modes are really being covered. So what I ended up actually thinking and discovering in this paper is to use another metric. And I wonder whether you like it or anybody has seen it, which is I take the minimum spanning tree of all the samples and the total size of that minimum spanning tree. And you can imagine, if you think about what is the minimum spanning tree of these samples, that the minimum spanning tree really exhibits whether you actually found these modes, because there must be one edge going from here to there in that minimum spanning tree, right? And I actually, these are these curves, which I didn't explain up here. So here you really see how the minimum spanning tree size increases with the number of samples. And there is interesting also relations to the dimension of the space being sampled and so forth. And also that if you have a minimum spanning tree of distances, you can actually really almost count the number of modes in that tree. Some detail you can find in the paper. Okay, with that kind of metric, I can actually now do a shoot-off of these kind of sample methods on a bit more harder problems. So we also introduced then some robotics problems. There are basic inverse kinematics problems where there's many ways to grasp. This is quite reddish, actually. I don't know why. Then some inverse kinematics problems where there is a big obstacle in the middle, where obviously you can grasp like this and this, and you want to, whether you can find these modes. But then this one is, the display is a bit, not so nice to parse, but this is actually pretty hard sequential manipulation problem where you first have to push away an obstacle, then grasp for the stick. Only then you can grasp for the stick and use that stick to touch another, like a yellow ball. The point is that these 4 steps are completely interdependent. So all of these 4 steps are completely, you cannot really separate these problems. And that's a typical example which has tons and tons of local optima and that are hard to solve. Okay. On these problems now, we can now do this experiment. So I ran a cluster with all of these, instantiations of methods that we could have. All, using plane gradient or Gauss-Newton gradient, or using noise or no noise, or using Metropolis Hastings or Wolfe, or using MCMC or Langevin or whatever, kind of like shooting off all of these kind of methods on these problems. And each of these methods is a little cross here in these plots. So we won't be able to parse these plots here. And point is just that for each of these methods, we can embed them in this performance plot and ask what is the diversity that they can generate per function evaluation, and how many samples do they give per function evaluation. And the good methods are actually on the top right here. Okay. Without being able to really like parse them here, you can actually see some patterns. And I maybe just refer to the paper. And here is eventually the findings. Okay. So a couple of things in this experiments didn't really pay off at all. For instance, like doing burn-in steps. That's kind of obvious that this doesn't really pay off so much. But then also using plane gradient steps almost never outperformed using proper Gauss-Newton steps. Also not surprising. In terms, maybe more surprising to the optimization coming from optimization. Usually backtracking line search and Wolfe conditions, Amintje rule, are super important to actually efficiently do things. But because here these samplers are so aggressive going downhill, and if they don't work, you just restart. Actually, it turns out that these rejection methods in these experiments didn't really pay off so much. And you just took every step full size and just aborted and restarted instead of that. Also, the noise levels didn't really pay off so much. What it was a clear structure was that these nonlinear hidden run methods, they were super efficient when there were lots of inequalities in these problems. For instance, on random LPs, so random linear programs. And also that manifold RT methods were super efficient on problems dominated by equality constraints, especially these robotics problems. And exactly on these problems where manifold RT performed really well, other methods like plane MCMC and Langevin and things like that performed like really poorly. And then there was also some surprising results in terms of like diversity and restarting, that this restarting with distance to the previous samples kind of only in certain cases worked and in others not. Anyway, so we really learned also something about the complexity of the problems actually that we looked at. Okay, now the actual conceptual discussion. So this was very technical work. It almost felt like homework. We had to do this, or I felt like I had to do this to learn something about how to do this sampling, right? But there is now some interesting things. So in all of this work, I was always thinking, is there any role for Lagrange parameters for this in NLP sampling? And well, I keep it short here. So, but I think in those methods, actually, I never saw an opportunity for using whatever, estimating Lagrange variables or using augmented Lagrangians or something like that, which is interesting. And now to the actual thing. So initially I thought, why not work with the diffused NLP? What is the diffused NLP? You have the NLP, which describes the feasible space and an energy in a feasible space. That describes, of course, a distribution, and you can diffuse that distribution, like as in diffusion models, right? And then if you can define the diffused NLP, you can also define a denoising of that diffused NLP. First result, turns out that you can analytically kind of approximate the diffused NLP quite well. And I got some equations for that. This is an example for diffusing like a box, just two inequalities to become, you know, the standard normal distribution and so forth. And also it eventually turns out to have some rather good approximation with some sigmoidal, actually product of sigmoidals. So how you can describe a diffused NLP. But the thing is then, if you want to use this diffused NLP and then think, okay, now I'm going to do like standard probabilistic denoising on that diffused NLP, it works like really poorly, like super, super poorly in comparison to anything that I showed earlier. And this was the initial idea that I had, and that I wanted to, like, you know, think this is cool, like doing model-based diffusion on a model-based sampling on a diffused NLP. The point is that the diffused NLP, the way I at least define is, I only define it based on local observations, on local linearizations and quadratic approximations of these functions. And so actually using this diffused NLP to define Langevin dynamics is actually super similar to using, looking only at a local SQP and then thinking that you can use Langevin dynamics to efficiently find samples of that SQP. The point is that this approximation has no global information and no target information. So you lose all these nice properties of, you know, denoising, diffusion denoising to actually cover global distribution. Okay, so this is kind of like the kind of story that really didn't pay off, at least in what I tried. I keep this short for the sake of time. So we also thought about, this is very sequential kind of methods. And I'm completely aware that instead of sequentially generating samples, it makes a lot of sense to generate them as a population, as for instance, with Stein variational kind of methods. And in the paper, I discuss a whole lot of ideas actually how to combine these methods. To conclude, so first, I think this topic of trying to think both sampling and optimization together, I find it super important, kind of. And I wonder really what is your opinion, whether you also like think, you know, these kind of works can really, you know, profit from each other. The second thing is that I think all of these methods are quite preliminary. I still think many of them could be made much more efficient, maybe tuning parameters more, many kind of things. And eventually, also, I think that here I only worked on algorithms and methods, but I think that could really have a lot of impact also to import and include these kind of diverse samplers in many kind of robotics problems, in particular TAMP. But I think having diverse samplers, efficient diverse samplers, could be a big changer actually in how we can solve problems in robotics. Okay, I don't know what this is, but thanks also to the co-authors. Thanks for your attention.
Hey, thanks for the talk. One question, because I was also recently looking in these nonlinear things for hit and run. Like, so, like the thing that I didn't actually try, because, right, you want this ray that you sample this direction, and then you want like the whole set in, like your allowed set on this ray. Like, do you formulate it in a way that you actually compute this kind of set for certain types of nonlinear functions, or did you find other ways? I mean, I can check it out, but I was just curious.
Thanks for the question. No, I certainly don't compute this intersection exactly. So all of the methods are tuned to be very, sample efficient or evaluation efficient. So they really try to use as little functional evaluations as possible. And so they really just sample there, and then if they see that it's violating, then it's approximating it locally. Yeah.
Next questions? So maybe one question from me about the link between what you did and the link that we can do between optimal control and RL methods, because there is a connection of sampling on one side and some on solving on the other side. Can you see a bridge between the two also?
Which
between RL and optimal control?
You mean reinforcement learning?
Yeah.
A tricky one. So I think like in reinforcement learning, the exploration is one of the limiting things, right? And generating diverse, that's another thing. Generating diverse manipulation is really a topic that I'm thinking about a lot. So these term solvers, usually they generate like one solution, but actually I would love if they could generate any possible manipulation. And I think once we would manage to do that, maybe we could use these kind of like ways to generate like many examples or like really explore the space much better to also help reinforcement learning methods to explore much, much better the space of possible manipulations. Yes. Yeah.
Okay. Thank you again, Marc.